In this section, we'll look at encoder-decoder data dependency through a practical data flow lens. That means tracking how information moves between the encoder and decoder, and how that shapes masking, attention, caching, and token-by-token generation. This is especially useful for LLM and AI engineer interviews, because once you understand the dependencies, the architecture becomes much easier to reason about and explain clearly. This topic matters in interviews because it's not just architecture trivia. It's a practical way to reason about how data moves through a model and what that means in real systems. You should be able to explain the inputs and outputs at each stage, why masking and alignment matter, how latency and caching affect serving, and how the model behaves differently during training versus inference. At the core, this pattern has two parts, an encoder and a decoder. The encoder reads the source sequence and turns it into hidden state representations that capture its meaning. Then, the decoder generates the target sequence one token at a time. As it does that, it looks at its own previous outputs and also attends to the encoder's representations through cross-attention. So each new token is guided by the source. Here's the precise data flow in 3 stages. First, the encoder takes the input sequence and produces a last hidden state with shape batch, sequence, and hidden dimension. Next, cross-attention connects those encoder representations to the decoder's queries. Finally, the decoder generates tokens autoregressively, one step at a time. The key point is that the decoder does not use the raw source tokens directly. It relies entirely on the encoder's representations through cross-attention. This slide highlights why encoders and decoders are asymmetric by design. The encoder reads the entire source sequence at once, with no causal mask, so every token can attend to every other token in parallel. It produces contextualized hidden states up front. The decoder works differently. It generates the target sequence autoregressively, using masked self-attention, so each step sees only earlier tokens, while cross-attention repeatedly consults the encoder's representations. Here are the key tensors to keep straight in sequence-to-sequence models. On the encoder side, input IDs hold the source token IDs, and attention mask hides padding. The encoder then produces encoder-outcoders, typically the last hidden state, which feeds the decoder through cross-attention. On the decoder side, decoder input IDs are the right-shifted targets, with decoder attention masked masking target padding. During training, labels compute the loss. During inference, past key values cache attention states to speed up generation. Cross-attention is really the core connection between the decoder and the encoder. At each decoding step, the decoder produces a query from its current representation. That query is compared against keys from the encoder's hidden states, and the corresponding values also come from those same encoder outputs, which were computed once up front. So in one line, decoder states create queries, and encoder outputs provide the keys and values. Here's the key idea. The decoder doesn't read the target sequence in exactly the same positions as the labels. Instead, we shift the target input one step to the right. That way, at each position, the model sees the previous correct token and learns to predict the next one. This is the basis of teacher forcing, and it keeps training aligned with the next token prediction objective. At each decoding step, the decoder draws on 2 sources of information. First, masked self-attention lets it look back at previously generated or teacher-forced target tokens, while a causal mask blocks any view of future tokens. Second, cross-attention lets the decoder retrieve relevant information from the encoder's hidden states. Those retrieval weights change at each target position, so the decoder can query the source differently as it generates each token. This slide shows how the decoder's dependence on the encoder has evolved. In simple sequence-to-sequence models, the decoder relies on one final encoder state, which creates a hard information bottleneck. Attention-based models relax that by letting the decoder look back over all encoder outputs. In transformers, Cross-attention goes further, giving the decoder access to the full sequence of token representations, so the dependency is distributed rather than compressed into a single vector. The key idea here is that encoder work is front-loaded. You process the input once, and those representations are reused. The decoder is different. It generates tokens auto-regressively, one step at a time, so latency really matters there. That's where past keyed values help. By caching key and value tensors for self-attention and cross-attention, especially the encoder side K and V computed once, we avoid redundant computation and improve both throughput and response time in production. One important caveat with encoder-decoder assembly is cross-attention initialization. The encoder and decoder may come from pre-trained components, but the cross-attention layers that connect them are often newly introduced, so they start with random weights. That means transfer learning is only partial here. To make the full model work well, those cross-attention parameters still need downstream fine-tuning on the specific task. Choose an encoder-decoder model when there's a clear mapping from an input sequence to a different output sequence. Classic examples include machine translation, where a source sentence becomes a target sentence, and summarization, where a long document is compressed into a short summary. It's also a strong fit for speech to text, since the encoder handles audio features and the decoder produces words. More generally, it works well whenever source structure needs to guide generation. Here are 3 common failure modes in encoder-decoder models. First, wrong masks let padding leak into attention, so the model uses tokens it should ignore and corrupts its representations. Second, bad label, shifting misaligns decoder inputs and targets, so each position learns the wrong next token and training breaks down. Third, if cross-attention layers are newly added but not fine-tuned, conditional generation collapses because the encoder-decoder connection is basically untrained. Here's the side-by-side difference between training and inference. During training, the decoder gets the right shifted target sequence, starting with a boss token, and uses teacher forcing, so the correct token is fed in at each step. Loss is computed across all positions, and those decoder steps run in parallel. In inference, the encoder runs once. The decoder starts with only boss, reuses past key values, and generates tokens one at a time. To be interview-ready on encoder-decoder models, you should be able to do 4 things. First, trace the key tensors and masks, including input IDs, attention masks, decoder inputs, labels, encoder outputs, and cached past key values. Second, define cross-attention clearly. Decoder states form queries, while encoder outputs provide keys and values. Third, separate training from inference. And fourth, spot common failure modes like bad masks, label misalignment, or weak cross-attention tuning. Here are the interview questions I'd expect on this topic. The key is to answer from the data flow. First, what the decoder actually uses at generation time. Then, how cross-attention differs from self-attention. Why targets are shifted during training, and what we cache during decoding, usually past keys and values, to speed things up. A strong final point is knowing when an encoder-decoder model is the better choice than a decoder-only model. Here are a few strong portfolio project ideas. First, build a summarization or translation system and clearly show tensor shapes at each stage, along with cross-attention patterns, latency, and common error cases. Second, compare a final state-only SEQ baseline with a full cross-attention transformer to quantify the bottleneck. And finally, add KV caching at inference and measure decoding speedups to demonstrate the encoder-decoder serving boundary. Here's the key idea. The encoder builds the memory, and the decoder consults it as it generates each token. At every step, masked self-attention lets the decoder look only at the target tokens it has already produced. Cross-attention then connects that partial output to the encoder's hidden states. So the dependency is conditional on the source, token by token, and it changes over time as generation unfolds. The key career takeaway is this: don't just name the encoder, cross-attention, and decoder. Explain the architecture as a data pipeline. The encoder turns the source sequence into memory. Cross-attention is the interface to that memory, and its quality often determines whether a system is truly production-ready. Then the decoder queries that memory one token at a time with clear attention masks, cache behavior, and distinct training versus inference behavior.